Test, test, test. That's funny. I guess that's muted this entire time. Alright, so we go in here, we're going to say number of virtual address bits 4. Just going to fill in all these blanks. 2 to the power of question mark is equal to 16k. To the power of 24 minus 1 is equal to m question mark m minus 1. Two to the power of question mark. This is equals, not minus. I don't know where the minus symbol came from. It's equal to 64t. And then 54 here. Okay. Let's go ahead and go down the bottom, say generate, and copy. Paste our table in here. So we've got 4 bits. So 2 to the power of 4 is equal to 2 to the power of 1 bit be 2, 4, 8, 16. Boop, 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 boop. Largest possible virtual address space would be 2 to the power of 4 minus 1 is equal to 15. Okay, so we have 16k, so it's going to be 14 here, which means we'll have 14 bits. This would be 2 to the power of 14 minus 1 is equal to, why did I say m? M minus 1. Well, that's megs. That's a SI prefix. Okay. Or SI prefix. Be 16k minus 1, right? This will be 24 bits. This will be 2 to the power of 24, which is of course 16m. Whoops. And then this would be 16m minus 1. And then this is going to be to the power of something is 64t. Okay. Well, 10 is k, kilo, mega, giga, tera. So that's going to be 40. And you have 64, which is 2, 4, 8, 16, 32, 64, 6. So it'd be 46, I think. Yeah, 46. So that means we have 46 virtual address bits. And then we'll have a 2 to the power of 46 minus 1, which will equal 64 terabytes minus 1. And then here we got 54 bits, so So 2 to the power of 54, which is equal to peta. And it'd be 16 petabytes. And then it's be 2 to the power of 54 minus 1, which is equal to 16 p minus 1. Okay. Let's check, see if we got those right. Alright, where are we at here? Solutions to practice problems. 9-1. Alright. This problem gives you some appreciation for the size of different address spaces. At one point in time, the 32-bit address space seemed impossibly large, but now there are database and scientific applications that need more. And you can expect this trend to continue. At some point in your lifetime, expect to find yourself complaining about the cramped 64-bit address space on your personal computer. All right, so we got 4, 14, 24, 46, 54. Okay, MTP, yeah. Hey, okay. Got them all right. That was easy. Okay. VM is a tool for caching. Conceptually, a virtual memory is organized as an array of n contiguous bite-sized cells stored on disk. See, this analogy I don't agree with. He used this in a lecture, and the thing that I wanted to say is like, well, what about machines that don't have disks? They still use virtual memory for protection and address space isolation. Like, are you saying virtual memory has to have a disk? Or are you saying that just that in the situation where it's used for caching, it has a disk? Yeah, see, there's 3 here. VM as a tool for caching, VM as a tool for memory management, VM as a tool for protection. So these sections are context specific. It's a tool for caching when you have a disk and you have swap space. Conceptually, a virtual memory is organized as an array of, it's not a general statement, of n contiguous bite-sized cells stored on disk. Each byte has a unique virtual address that serves as an index into the array. The contents of the array on disk are cached in main memory. As with any other cache in the memory hierarchy, the data on disk, the lower level, is partitioned into blocks that serve as the transfer units between the disk and the main memory at the upper level. VM systems handle this by partitioning the virtual memory into fixed size blocks called virtual pages. Each virtual page is p is equal to 2 to the p bytes in size. Similarly, physical memory is partitioned into physical pages. Also p in bytes in size. Physical pages are also referred to as page frames. At any point in time, the set of virtual pages is partitioned into 3 disjoint subsets. So we got unallocated, cached, and uncached. Unallocated pages that have not yet been allocated or created by the VM system. Unallocated blocks do not have any data associated with them, and thus do not occupy any space on disk, or anywhere for that matter. Cached, allocated pages that are currently cached in physical memory. That would be your resident set, I think. uncached, allocated pages that are not cached in physical memory. That's stuff that you've swapped. Example in figure 9.3 shows a small virtual memory with 8 virtual pages. Virtual pages 0 and 3 have not yet been allocated yet, and thus do not exist. That would be this one and this one. On disk, virtual pages 1, 4, and 6 are cached in physical memory. Pages 2, 5, and 7 are allocated but are not currently cached in physical memory. Okay. DRAM cache organization. To help us keep the specific caches in memory hierarchy straight, we use the term SRAM cache to denote the L1, L2, and L3 cache memories between the CPU main memory, and the term DRAM cache to denote the VM system cache and caches virtual pages in main memory. The position of the DRAM cache in the memory hierarchy, it has a big impact on the way that it is organized. Recall that DRAM is at least 10 times slower than an SRAM, and that disk is about 100,000 times slower than DRAM. Thus, misses in DRAM cache are very expensive compared to misses in SRAM caches, because DRAM cache misses are served from disk, while SRAM cache misses are usually served from DRAM-based main memory. Further, the cost of reading the first byte from a disk sector is about 100,000 times slower than reading successive bytes in the sector. The bottom line is that the organization of the DRAM cache is driven entirely by the enormous cost of misses. Because of the large miss penalty and the expense of accessing the first byte, virtual pages tend to be large, typically 4 kilobytes to 2 megabytes. Due to this large miss penalty, DRAM caches are fully associative. That means any virtual page can be placed in any physical page. The replacement policy on misses also assumes greater importance. Because the penalty associated with replacing the wrong virtual page is so high. Thus, operating systems use much more sophisticated replacement algorithms for DRAM caches than the hardware does for SRAM caches. These replacement algorithms are beyond our scope here. Finally, because of the large access time of disk, DRAM caches always use write back instead of write through. Hey Nerdenough, sorry I missed your message there. I had my mic muted for a while. Applied to around 100 jobs, only one interview that by reference and got rejected from to shit, man, that sucks. I'm doing pretty good. How are you doing? I made a lot of progress on this computer systems book. You can see I kind of like only have a small little bit left to read. I'm on chapter 9. This will be the last chapter that I read. The remaining chapters are on concurrency, network programming, and system level I/O. And all three of those topics, I feel like I already know substantial amount about, so I'm going to skip them. The concurrency section, I also have a book upcoming on my Learn log. This might be new for you, but I created this repo called Learn log. I forget if you saw this or not, but I planned out like all the stuff that I'm going to be doing for the rest of the year. So zoom in here a little bit. So these are all the categories that I wanted to improve upon. So heterogeneous computing, performance, security, general like computing, AI, ML, compilers, languages, interview prep, and mathematics. And so I just put in all those resources of things that I wanted to do into these categories. This is just kind of like an exercise that I did. And then I drew out this timeline of the months and weeks of the year. And then I just started placing things into the timeline with estimates based on my average reading rate and how I felt that I might be able to get through this stuff into this little calendar here. And I have a week off in June for travel. But for the most part, you know, I got just solid time to work on all this stuff. Just okay trying to catch a job. Yeah, man, that sucks. Did you get feedback from your rejection? I got rejected at the end of 2025 for a job that I was applying for, and they didn't give me any feedback. That always sucks when you don't get feedback, because it's like you don't really know how to improve or how to adjust your strategy. Yeah, a lot of companies don't do feedback from what I gather. That sucks, man. Well, I mean, there's only one thing to do is keep on trying. Yeah, I allocated 2 months for this computer systems and program perspective course, but I think I'm going to finish this whole course by the end of the second week of April. So I'm actually ahead of schedule 2 weeks here. So that's exciting for me. I'm getting things done. I also started on this Linux binary analysis book last week, which I think I discussed with you at some point. This guy right here, the Elf Master. I got to chapter 2 on this. And I feel like a lot of the things I've learned in this computer systems book is feeding directly into binary analysis, because I learned a lot of assembly, disassembly, like analyzing programs, reverse engineering with GDB. There is a really cool lab that I did. If you go under the course here, so this is the repo that I have for the course CSAPP. There's a directory here, labs, and it's called the attack lab. This might be something that interests you. The whole idea with this lab is that there's these two programs, C-target and R-target, and they're both vulnerable to stack overflows, but one of them has memory protection on it. The R-target has memory protection. So while you can still write to the stack using the Stack Overflow, you can't actually execute from the stack because it has execution protection. So you have to do this thing called return-oriented programming. But this is a lot of GDB. So if you're interested in that, there's a repo. If you go here, I forked it from this repo here. This B Madone CS APP Labs, and then you go to attack. It's a pretty cool lab if you have the time. I learned a lot from it. That's the only reason why I'm hyping it up so much. Yeah. So yeah, the binary analysis book. it's touches on a lot of stuff that they touched on in the chapter on linking. So the CSAPP book has a chapter on linking here. And so I read this whole thing. I don't think I did any of the exercises here because I kind of know a little bit about linking already. Enough to like not feel like I needed to do the exercises. But yeah, I mean, they talk about all the same things that they talk about in this binary analysis book. I learned when I read this chapter on linking, I learned a lot about position independent code. Like I knew about position independent code in theory, like a little bit. Like I would say like maybe 10% of what I needed to know. And then actually reading this chapter or reading this section of the chapter, I fully understand the global offset table, the procedure link table. Like I fully understand how shared objects get mapped into processes and relocated dynamically. So yeah, this is like a really good chapter, this linking chapter. Linking is like an area of programming that like most people don't spend a lot of time with, but I think it's really important for understanding how programs actually run. Yeah. I mean, I'm also in that boat where I'm not working right now, so yeah. I also have all the time in the world. So how Instagram had millions of likes and they got all sync live. All these comments got fetched and feed into posts with so accuracy. I saved this question to ask for you. Let's see. Was it like a systems design problem? Yeah, that sounds like a systems design problem, which you'll get in interviews. Um, Generally with likes, there's not a high degree of consistency. They prefer availability. So if you're not familiar with this, there's something called the CAP theorem. You can read about it. It's pretty straightforward though. Like at any given time, you have a trade-off. There's three things: consistency, availability, and partition tolerance. And at any time, you get to choose two of those things. You can't have all three. And so, and the other caveat is like you're running usually on a distributed system, and so you need to be tolerant of network partitions. So really, it's a trade-off between availability and consistency in most situations. And so with likes, because the data doesn't need to be highly consistent, they make trade-offs for availability. And so likes get written into a highly available, relatively lower eventual consistency data store usually. And then as far as comments, so comments are indexed in a database by the post ID if it's a relational database. And with indices, it's like a O of 1 operation to access things by index. So it's like really efficient. So I would say like if you're doing a traditional relational database for posts, you would index based on the post ID, and you'd have a comments table that's also has a foreign key to post ID, and that comments table would be indexed by post ID as well. And that way you can just select on that table all of the comments for a given post. And then the other thing you might want to do is sharding, which is a more nuanced topic for scale. Like as you're scaling up a system, you need to be able to like basically sharding is like partitioning your data into different instances of the database based on your access patterns. So if you have a global network of clients that are all accessing posts, maybe you shard by post ID. and then have some type of caching in front of that. I mean, 99% of scaling a service is caching. And that's something that I've learned now in this computer systems book, is that 99% of scaling computer systems themselves is caching. Like we're reading right now about caching for virtual memory. And I read a whole lot about caching for like SRAM caches for CPUs, cache lines. Like the way computers scale is through and perform well is through aggressive caching. So yeah, that would be my general approach to discussing the problem that you proposed here, is to first talk about how to ingest the data into a storage system efficiently, making the trade-off for availability, and then how to then effectively query that data, with indexing, with sharding, and with appropriate caching. And the strategies that you would have for caching. There's so many different avenues that you can go down in systems design problems. It really is up to the interviewer to kind of like indicate to you where to go and where not to go, where they're interested in going. But it's on you. It's the responsibility is on you to ask those follow-up questions and to ask the interviewer, is this the path you want to go down? Because in any systems design interview, you can go down any number of paths and spend the entire interview just going down that path. So it really depends on what the interviewer wants, and it's up to you to ascertain what they want. It's kind of a difficult process. I do have a bunch of books on systems design that I picked up. I'm going to go grab them right now. One of them came in today as well. I'm really excited about. So these are the 4 books that I picked up that have some systems design stuff. This one I've had for probably a decade now. So Cracking the Coding Interview has a section on systems design, which I will be reading later in the year. It's on my list. This is a 2-volume series called Systems Design Interview and Insider's Guide. So there's the blue book and the green book. And both of these came highly recommended. I've leafed through volume 2 because that was more recommended. And it isn't necessarily my cup of tea, the problems that they're solving, but I think it would be good practice. And then this is the book that came in today. So this is an infamous book called Designing Data-Intensive Applications. This is a book that pretty much everyone who does any systems design stuff has read. It's a good book for interview prep for systems design, and the second edition was just released. So if you're searching for the PDF, you might want to look for the second edition. This looks like the original. The second edition is the new modern O'Reilly covers. They have a different design about them. This is probably the older one. It's going to be hard to find, to be honest. It's going to be hard to find the PDF for the new one because it was just released. But the second edition... Oh, look. It was so hard to find. I just Googled for it and it showed up. So yeah, this is the second edition here. I'm going to go ahead and download this because I'll need it later in the year when I read this on stream. I will be going over this book later in the year. But let's go ahead and pop it open here. But yeah, let's go to the table of contents. And you can see why it's like valuable here. So trade-offs in data system architecture. It's not just about data, even though it's data-intensive applications. Defining non-functional requirements. So this is like a terminology. This is a language that's used in this culture of systems design, functional and non-functional requirements. So that's usually something that you prompt the interviewer for when you start on the interview, is to figure out what the functional and non-functional requirements are. Data models and query languages, storage and retrieval. They cover B trees, encoding and evolution, the different encoding formats, replication, single leader, multi-leader replication, leaderless replication, sharding. So the topic that I just brought up earlier is like really important. They go into detail on that here. Transactions, isolation levels. So this ACID is like another acronym for atomicity, consistency, durability is the D, and I is, I think, independence or isolation. So it's atomicity, consistency, isolation, durability. I think that's what it is. ACID databases. Yeah, atomicity, consistency, isolation, durability. So atomicity is like doing things, performing operations in a way that they cannot be interrupted, or if they are interrupted, they're rolled back. So that's basically your transactions in databases. Consistency is like if I perform a write and another concurrent connection performs a read, that read sees the same data that they see the same data that I wrote. Once my transaction is committed, I'm able to read that. Isolation, durability are other things that we can get into, but let me just go over the rest of the book here. Consistency versus consensus, overview of distributed system problems, batch processing, stream processing, more streaming, and then a final chapter there. So yeah, lots of stuff here, but yeah, that's a good book if you want to pick up more systems design stuff. So if you were given a problem and technical phrase of the interview, how would you start? What would you go through technique? What will be your go-to technique is when you start analyzing the problem on where you didn't have work in the past or at all. I would just ask questions. I think the best thing to do in interviews is to ask clarifying questions. So you're giving a problem statement usually. Your first thing that you should do is write down all the important information in the problem statement. So if they have a certain requirement around throughputs, like requests per second, or they have a certain requirement about durability or scale, or any of these like different aspects of designing a system, whatever the requirements of that are, just write down those requirements. And then you can categorize them as functional and non-functional. Functional are things like, requests per second and stuff like that. Non-functional are things like security, auditability, like these kind of like less engineering heavy stuff. Instrumentation, observability. There's like all these different non-functional requirements. So if they don't prompt you about those, you can spend some time prompting the interviewer about those. But just asking questions, like following your curiosity, asking clarifying questions is like the most important thing that you can do in a systems design interview, in my opinion. Because that'll show that you're interested in the problem and that you're interested in learning more about what type of solution that they need. And it's all make-believe anyways. It's a system design interview. It's all make-believe. So usually when you ask really good clarifying questions, sometimes you can catch the interviewer off guard because they're like, oh, I didn't think about that before, or I never had a candidate ask me that question before, or go down that path. And oftentimes that'll put you ahead of the competition when you're competing for a position, which in this market you kind of have to do stuff like that. Like you can't just roll into an interview and expect, based on your own like charisma, although charisma is important, to be able to outperform the competition. A lot of these jobs, they're getting really highly competitive, and you need to know what the fuck you're doing. At least that's kind of like my approach. I mean, you don't have to know everything, but basically like my understanding of the job market right now, which is not great because I'm not working right now, but I elected to not work. I'm not working, not because I was forced to not work. I chose not to work. But it means that my understanding of the job market has kind of like drifted a little bit from when I was interviewing and working. But my understanding is that AI has put pressure on a lot of these entry level roles. So beforehand, you could just like roll into an entry level role and then grow within the organization, grow within that role, and become a higher level senior, staff level engineer. Nowadays though, because those entry level roles have been kind of like knocked out, like a lot of companies are just not hiring below like L5 or even L4. So if you're hired at that level, or if you're trying to get hired at the level, there's just not a lot of open recs for that level. So you gotta like basically be at an L4 or L5 to get into some of these companies, and that just requires a lot more effort, unfortunately. But I mean, at the end of the day, like it's not like an insane amount of effort. And if you optimize your strategy for study, you could probably get through with like a month or two of interview prep. That's what I did in the previous phases of my career, is that I basically, at the end of my tenure at a specific company, if I felt like I wanted to start looking at other companies, I would basically just take 1 or 2 months where I just like crack the books and I go through and I find the important stuff that I want to learn to prepare for interviews. And then I would just study that stuff. And this book was really valuable, Cracking the Coding Interview. So if you're going to get one book for interviewing, for software engineering, that is, it would be this book. But I don't know what the type of roles that you're applying for, what you actually want to do with your career. Cracking the Coding Interview is for software engineering. Let's see, Cracking the X Interview. So this is the one for software engineering here. But there's also one for like, is this beyond Cracking the Coding Interview? I've never even read this, but I want to. This is a little bit more recent. So this is published in January of 2025, whereas this one was 2015, so a decade before. These are the systems design interview books that I mentioned. These two here. Let's see here. There was another one that she wrote. Yeah, Cracking the PM Interview. So she's a product manager. And then Cracking the Tech Career. Insider advice on landing a job at Google, Microsoft, Apple, or any top tech company. So this is probably less about interview prep and more about actually landing the job offer. So when taking an interview for entry level or mid level, do you move with problem solving or the skill? And what's your take on it? So I started as a security engineer, but the market here is penetration testing and consultancy. Well, if I was in your shoes and I wanted to, I assume you want to take on pen testing. Is that correct? Or do you want to focus on security engineer? Like if the market is asking for pen testing and you're and you enjoy doing that sort of thing and you want to lean into that, what I would do if I was in your shoes is I would just start doing a lot of these. I mean, again, I'm not in this space, so I'm a little bit ignorant here, but I would start doing a lot of these capture the flag exercises. So if you Google for like just GitHub capture the flag exercises, I'm sure shit will come up here. Awesome. I think I remember seeing this one before. Awesome CTF, a curated list of capture the flag frameworks, libraries, resources, and software. Let's zoom out here, or it's full screen. Attacks, reinforced cryptography. So this is all about capture the flag exercises. And the whole goal is to like find some type of special magic number or a string somewhere inside a binary or what have you. You know, I've only done a few of these. Again, I'm speaking from ignorance here, but I would be spending a lot of time doing this type of stuff. It can be really fun. So you mentioned, I think you mentioned before that you use Kali Linux. So they got stuff. I'm sure this is not like anything new to you, but there's a lot of resources around doing capture the flags for different areas. But it sounds like you got stuck on this systems design interview, which isn't uncommon. So if you wanted to get better at those things, I think you would probably do really well with this book. It's a big book, but what you can do is just like crack it open and find the areas that you want to focus on. So let's find a PDF for this. Cracking the coding interview PDF. GitHub. Man, GitHub just has every PDF for every tech book. It's like the amount of piracy on GitHub is insane. Let's download this one. Hopefully these don't have viruses in them. You know how PDFs can sometimes like have like PostScript code in them. All right. Oh, this one's it's because I have inversion on it. Let's turn that off. All right. So, this is an actual scan. Nice. I actually like the scans when people do scans. So yeah, I mean, like you can look through the table of contents here and maybe just select the areas that kind of jump out to you. So you might have something like the overall interview process I want to know more about. So I'm going to read, that's only 8 pages. You know, I'll definitely read that. Before the interview, I'll read that. Behavioral questions. This is an often overlooked area of the interview, is the behavioral questions. So doing some preparation around that is like important, because a lot of highly technical people, they have difficulty communicating, they have behavioral issues, and they don't improve in those dimensions. And so if you improve in those dimensions in your communication skills, and your ability to kind of do things other than technical things, then that kind of sets you apart. Because if you're equal to someone else on a technical level, or even slightly below them, but you blow them out of the water on behavioral stuff and communication skills, that's going to set you apart. Because at the end of the day, people want to work with other people that they can effectively communicate with. Like, you don't want to be working with someone who just frustrates you because you're having difficulty communicating with them, or they're an asshole and they don't know how to like politely interact with other people in the workplace. So behavioral questions is definitely like an area that you could like, you know, and this is not a lengthy treatise on the subject. It's just like 4 pages here. You know, getting an overview of like Big O and asymptotic complexity, I think is just like a good thing to have in your tool belt, because it's just so essential to everything that you do as an engineer, or really anything in technology. Even outside of, I noticed outside of technology areas, people are starting to use Big O terminology. So it's super common. So it would be good to have that in your belt if you don't already. These are just like different strategies for technical problems, I believe. And then this is just a huge collection of interview questions. So you got arrays and strings, linked lists, stacks and queues, trees and graphs, bit manipulation, math and logic puzzles, object-oriented design, recursion and DP, system design. So this is what we were saying before. Your question was around like systems design and scalability. So this will give you like a blueprint for handling that question that stumped you. Or I'm not saying it completely stumped you, but possibly was an issue when you were interviewing. Like just read this section here. It's 37 to 143. That is literally 6 pages. And you'll have at least a little bit more of confidence around doing these problems. Sorting and searching, testing, knowledge base, C and C++, Java, databases. So some of these things you're probably just not going to be interested in. They're not relevant to your interests or the pursuits that you have in your career, and you can just skip over those. Don't feel guilty about skipping over stuff. Like you got to focus in on the stuff that's important, you know? So maybe database is important for the thing that you're doing. And maybe threads and locks are totally not important, you know? And then they have solutions in the back of the book. What's funny is I would never consider topological sort as an advanced topic. Or even Dijkstra's algorithm. Yeah, I wouldn't consider some of these. I mean, these are like still super beginner to intermediate things. They're not super advanced. What else? Yeah. So yeah, I mean, I would recommend just getting this PDF downloaded, cracking open at least the system design part, and then also kind of like looking at different areas of the book that interest you. So I have another question. When you apply for big companies like AWS, Microsoft, Tesla, Google, what they see in the CV and the person cause majority get rejected even prior to the interview? Possibly. In my experience, and of course, everyone's experience is different here. So immigration status is like a big factor now because of, you know, the new administration in the United States, but you're not looking for jobs in the United States. But for the most part, like when I've interviewed people, I've interviewed at least 500, if not more. I would say 500 to 700 candidates I've interviewed in my career. And that's from like basic technical screeners to like systems design to, you know, in-depth technical problems. I've done pretty much every aspect of the technical interview as an interviewer. And I've only looked at a resume out of like 500 candidates. I would say maybe I looked at a resume 10 times. So 10 out of 500. A lot of times I would say the resume is to get you noticed by a recruiter, but the person who's actually making the hiring decision, oftentimes they don't even look at the resume. They're looking at the candidate. They're looking, can this person do the job? Will I be happy with them in this role at the company? Are they competent? Do they have evidence of their competency? Which is, you know, things like, you know, I have these 3 side projects that I've been working on, you know, for the past 6 months, and I've done XYZ to better my skills, and you know, I've solved these problems at this company, and so on and so forth. Like, is there data backing your competency? Because people can present as competent in a technical interview, but do you have like further data to actually demonstrate that you're competent? Those are things that interviewers look for, the people who actually make the hiring decisions. CVs and resumes are more for recruiters. For the most part in technology, your pedigree, like your education, your work experience. Years of experience has an impact, obviously, on compensation. Years of experience has an impact on your viability for a specific role, because some roles actually do just require experience. But for the most part, if you can do the job, you demonstrate that you're competent in their interview, you're good at communicating. You, of course, pass all of the interviews. You demonstrate your competency. I think like that's the best you can do. I wouldn't worry too much about like having the exact right thing on your CV. I basically have a CV template, and every time I apply for a company, I'll like customize it a little bit for the role, because I have so much work history. This might not be apply to your situation, but in my situation is that I have so much work history, it doesn't fit on a single page. And the rule is your CV should be one page. It's the one page of things that you're showing the recruiter and potentially a hiring manager. This is the one page of things that I'm really proud of. It's your brag doc, your one page brag doc. You're like, I worked at this company, I accomplished this thing, I went to this school, I did this project, I got this grade. All the things that you're proud of in your work history, that's what you should be putting on your CV. And it's going to be different for every company that you apply for. So I have a template, and I customize the actual content of that template every time I apply for a company. And the idea is that I'm imagining myself in the position of the hiring manager. I'm making a decision about this role. They've already posted the requirements for the role. So it's up to me to like show them the data that they need to feel confident that I will be able to perform in this role. And so some people, they have a CV that they just send out photocopied to 100, 1,000 different companies. Like that's just not going to cut it. Like you need to target your CV. It's like, these are the exact things that is showing to you that I can do this job, versus, these are just some things that I put on my CV, that apply to any company. So I would recommend catering your CV every time you apply to a role. Have that CV reflect data that demonstrates that you are able to perform that specific role. So if the job is about penetration testing, like have a number of things in your CV that just demonstrate, I have done these capture the flag things on GitHub. I have done, I have gone through these courses online that show, competency with different technologies and penetration testing. I've used Metasploit to exploit systems in a lab environment. Just have like a whole list of things that you've done that relate to penetration testing. And then also, you can throw in stuff in there that shows that you're just generally competent. Like, your academic background, whatever your school is. If you did really good in school, you can put that in there. If you don't have a lot of work history, or if you do, if you delivered some huge outcome at a company, like put that in there. Even though it's not relevant to the role, it does indicate that you have competency, general competency. But yeah, that's like my general approach. Can I share the template? It has a lot of personal information, so I'm not too eager to share it, but I might distill it down into a template that is anonymous, if you feel like that might help you. Yeah, I mean, you say that you're not doing this. Most people are not doing this. Most people take their CV, they work on it for maybe like 30 minutes to an hour. They maybe have someone like look at it, do a sanity check, and then they just photocopy it out to all the different companies. The other thing I would advise you, if you can make this happen, is to network. Find opportunities to socialize with people who are working in the fields that you're working in. Because when it comes time for them to hire someone, they're going to think of you. or they're going to reach out to you and say, hey, do you know someone? That's what networking is about. People at companies prefer to hire people that they know and that they have worked with in the past, and they have demonstrated competency. Because when you are interviewing randos off the internet, there is a lot higher risk that that person is not going to perform well. Versus if it's someone that you know in your professional network, there's a much higher chance that they're going to perform well. Especially if you've already worked with them, you already know that they perform well. So that's something that I would try to do as much as possible, is find opportunities for networking. And it sounds like, like when I was younger, the last fucking thing that I wanted to do is go to a networking event. I hated that stuff. But what I found out is like my form of networking, that's because I was trying to do someone else's style of networking. My style of networking was to go to these meetups. If you just go to like meetup.com and search for something you're interested in. So I'm interested in Ghidra or reverse engineering. We'll say reverse engineering. Of course, none of these are tech related. Technology. Okay, we have way too many AI meetups. Let's see, reverse engineering meetup in Colorado. Den Hack. So these are like hacker spaces, but a lot of these hacker spaces have meetups, and you just go there and you talk to people. You get to know them, you get to know what they're working on, and like I would say 99% of the people that I met through meetups, I've never taken a job or had a job offer through, but that 1% I have. I have made really good contacts. I've had several job offers through just going to meetups. And another thing that meetups have is like, well, these are general hacking meetups. Let's see. Let's click on this group here, or this page here, see what it's about. All right, well, I'll just do this one as an example. So let's go into this open house one. So this is more like an open house for the hacker space. It's not a good example. Let's see if they have any past events here. This might not be a good meetup as an example. Anyways, the thing I wanted to mention is that a lot of these meetups will have opportunities to give presentations about stuff that you know. Oh, a one that I've done recently was Colorado Linux user group. Let's do, where's the past events here? So System 76 is a Linux vendor here in Colorado. These are install parties. So Nix OS meetup. So I don't do Nix OS, but like conceivably, like if you are interested in Nix OS, you could give a presentation on something related to Nix OS at the meetups. And what that gets you doing is whenever you give a presentation on something, you are forced to really understand it, because you don't want to embarrass yourself in a public venue like this, even though it's a bunch of like nerds in like a small room in some like, hacker space. Generally you just don't want to embarrass yourself. So you will put forth the effort to understand that thing that you're giving a presentation on. So you have an opportunity for learning, in-depth learning. You get to present material, so you get to teach other people. And the third thing is that you get really good at communicating. So when you have to present ideas to other people, you have to become an effective communicator. You will develop communication skills. So I always recommend people go to meetups, not only for the networking opportunities, but also to become a better communicator, a better speaker, and to learn and grow. But yeah, that's just some things that I wanted to throw out there. Let me send you the things that we talked about, the books at least, because I know you mentioned that you wanted to get the links. So I will send you, let me send this over to here. This guy, I don't want to overwhelm you though, but I will send you a couple links. This one I think is a good one for systems design, specifically. Cap theorem is a good thing to be familiar with. And then this attack lab. So I'll send you all these links here. Let me just copy them over here. And man, like, I know you can be bummed out when you don't get the job offer, but it's just gonna happen, man. Rejection happens. It fucking sucks. You gotta eat it and move on. I always like to think of it as like it's their loss, because you're a good candidate. You would have performed exceptionally well in that position. You would have delivered value to that company, and they're missing out. It's their loss. So don't even think of it as a rejection. Think of it as this company has demonstrated that they're not a good match for you, because they're so stupid that they weren't able to pull the trigger on giving you an offer. Okay, that's a bit of a weird URL, but I'll go ahead and send these to you. So I'm gonna write this. I'm gonna write it to my jump drive. And then, was it run? No, var run? Yeah, var run. What is all this stuff? Where am I at here? Run media. There it is. Okay. So I want to write it to run media C0 wiped, and then links.txt. All right. I'll get that loaded up here. Send over to you. Let's close out of that. I'll write that out. And then, yeah, let's switch over. I'm going to switch over to my other PC here just to send you these links so I don't forget. All right, I'll paste them in Discord. Well, I'll paste them in the Twitch chat and Discord so you have them. That link got broken, but I'll post them in Discord here. Give me 1 second. And then maybe I should give them like descriptions here. So this one is a fun GDB attack lab I did. I have the solution. if you want to compare notes. Oh, that's the wrong one. Oh yeah, that's the right one. All right, that's a lot of links there, but I pinged you on Discord with everything. So anything interesting you while reading this book, which kind of help you analyze problems differently in that context? Which book? The computer systems book? This computer systems book, it's just a good fundamentals book on how computers work. Like, I feel like I should have read this at a much younger age. And everyone who is a programmer or works in technology at this level should really have this type of foundation. It doesn't have to be this book, but the main skill that I got from this book is being able to disassemble a program in GDB or with objdump and be able to look at the assembly and just like decipher it line by line. And so now I know all the general purpose registers. I know the multimedia extended registers, the SIMD instructions. I know all the general integer and pointer instructions, load effective address, all of that stuff. Like I got really good at just looking at assembly and figuring out what the fuck it's doing. And I did that, through obviously through reading the book. That gave me a lot of opportunities to do that, but also the labs in the book kind of forced me to do that. And then the big tool is GDB, the debugger, because when you're giving a binary and you don't have the source code for it, and there's no dwarf debug info, and all the symbols have been stripped from it, like all you're left with is a bunch of instructions. And how do you make sense of like what this program is doing from just the instructions? Well, you single step each instruction in a debugger and you observe the impacts of those instructions on registers and memory and the flags, the CPU flags and other bits of processor state. And in doing so, as you single step through programs, you begin to understand, oh, these are the patterns. You begin to see some patterns in how compilers turn source code into assembly and machine instructions. So that was like the big skill that I got from this book. And I'm happy I did that. I did spend a lot of time on the first 3 chapters. If we go over here, so the first 3 chapters, this chapter was really lightweight. It wasn't very involved at all. But once you got into part 1, program structure and execution, let me actually make this a little bit bigger so we can step through it. This section, these 3 chapters here, actually just these two chapters here, representing and manipulating information and machine level representation. Those were really involved chapters. I mean, you can just look through the text here. You can see, like, you're looking at instructions. It's like, these are the assembly instructions. This is the byte encoding of the assembly. This is the offset into the binary or the memory, depending on which tool you're using. And it's like, you got to figure out what the hell it's doing from the instructions. And sometimes they give you the C source code and then they compile it and then they show you the output. So you can kind of learn how things map to each other. But a lot of this is just like looking at assembly and figuring out what the fuck it's doing. And so that was like the big, and look, like, you know, they have these diagrams for like the general purpose registers. This is a diagram that I have earmarked. So I have all these earmarks in the book. And this is a diagram that I had earmarked because when I first started learning assembly, I didn't have this diagram. And so I was constantly confused, like, what these different register names meant. Like, I knew they had some type of relationship with each other, but this has all the information that you need. So RAX is a 64-bit register general purpose accumulator. EAX is the 32-bit version of it. AX is the 16-bit, and AL is the lower 8 bits of that register. And it's typically used as the return value, or in the case of a syscall, it is the syscall number that you're using to invoke the kernel. So you can see how things relate here. So these are all the general purpose registers, 64-bit, 32, 16, and the low order 8. And then on the right hand side here, there's little comments about what they're typically used for. So the thing that would always confuse me is like the calling conventions in C, or really in any language. There's specific calling conventions, the sysv ABI, application binary interface. And I knew of that, but I didn't know the details of it. And so this kind of like just shows you, okay, well, EDI would be a 32-bit register that stores the first argument to the function in the C calling convention. And then they have notes on whether it's callee saved or caller saved. So you can see some of these are caller saved, some of them are callee saved, which is important to comply with the application binary interface. If you don't save registers at the appropriate location, either caller or callee, then you're going to have corruption. You're not going to be able to cooperate with other functions. And then, of course, the stack pointer, RSP, ESP. Stack pointer always has SP in the name. So it's easy to see, okay, that's a stack pointer. What else? So these are the general purpose registers, but then there's also the multimedia registers, which are used with SIMD programming. And I learned a lot about those. I think there's a table somewhere here. Maybe I hallucinated that. It's somewhere in the book, but yeah, these two chapters are really solid. I'd recommend anyone who wants to learn how computers actually work, especially x86 64-bit architecture, to read these. This chapter I skipped because it's about a fictional instruction set architecture that they invented that I really don't give a shit about. Optimizing program performance. I learned a good amount in this book, or in this chapter, about general optimization techniques. Some of these, like reducing procedure calls, eliminating loop inefficiencies, these are like common sense things that you would do naturally. But some of them require an understanding of the microarchitecture of the CPU, of the instruction set. And that gets into things like enhancing parallelism, where you have all these functional units inside of the CPU core, and you're trying to optimize for throughput and to saturate all of those functional units to keep them working as much as possible. Every clock cycle, have them doing some type of work. And that requires a level of understanding of the microarchitecture that is like beyond what most people actually keep in their head. So I got a lot out of this, understanding the enhancing parallelism. Some of this stuff was really useful. Loop unrolling. So that was like a general technique that I was familiar with from my work in BPF. But yeah, I mean, this just goes over all the different ways that loop unrolling can help performance. What else? So this type of parallelism that they talk about is what they refer to as instruction level parallelism. So I learned there's 3 types of parallelism. There is thread level parallelism, which is what I'm familiar with, where you create separate operating system threads and they operate in parallel. They have different execution contexts running on different cores, CPU cores. So that's one form of parallelism. But then there is another form of parallelism, which they refer to as instruction level parallelism, which is basically like when you write a program, the dependencies of data in your algorithm sometimes allow for parallel execution. A good example in the book, they might not have it here, but a good example would be like if you have like x times y plus z times a. So this is one expression that could get evaluated in many different ways. But what you can see here is x times y is totally independent of z times a. So you can execute this as x times y, and then as a second step do z times a. And then as a third step, we'll say temp 1 is equal to that. We'll say temp 2 is equal to that. And then we say temp 1 plus temp 2 or something. So we could order it that way. We could reorder these and it's still correct. And most importantly is that we can do these 2 multiplications in parallel. And so what does that mean? Because a single core doesn't allow for parallel execution, but it does. It's just not at the instruction set architecture level of understanding. If you understand the microarchitecture, you understand that CPUs pipeline instructions, CPUs do out of order execution, CPUs do speculative execution, they do branch prediction. They have multiple functional units that can be operating on data that's independent of each other at any given time. They have whole sets of registers that are unavailable to the instruction set that do speculative execution and hold temporary state, evaluating temporary state further ahead in the program than where the current state is currently at. So there's all this stuff with microarchitectures that they dive into here. So this is really great for optimizing program performance. The memory hierarchy was really great. Learning about caches. Like I knew about cache lines and how to write algorithms so that they optimize for cache access, cache hits. Like you want to access data that's in the CPU caches. Like you don't want to have to go all the way out to main memory. And so in order to do that, you need to exploit a property of systems called locality. So spatial and temporal locality, they go all into that. So they have a whole section here on locality. How to write cache-friendly code. They showed an example of like a matrix operation, and you just reorder the way that you're accessing the matrix, and it just dramatically improves the cache efficiency and the overall performance of the algorithm. They actually had a lab that I did that required me to implement matrix transpose and optimize that for cache access, which I did. So memory hierarchy was really great. Linking was great to learn a lot about ELF binaries and how dynamic linking works. I mentioned before position independent code. Exceptional control flow was this chapter that I just finished. That was great as well. I mean, some of this was already reviewed for me. So these 3 sections down here, signals, non-local jumps, and I think process control. I skipped the reading on. No, yeah, process control, signals, and non-local jumps. I already knew a lot of this, so I skipped that. I could have skipped this as well, but exceptions I got a lot out of. I'm glad that I read that. And now we're on virtual memory. And this is the whole point of me reading this book, was for virtual memory. So yeah, lots of good stuff in this book. So this will be great for one who is going to get into the malware analysis and reverse engineering. I mean, this book teaches you about computers, how they actually work. From a microarchitecture level to the instruction set architecture level, all the way up to the Linux system call level, and even above that, they cover libc APIs. So that whole level, whole set of levels there, they teach you about in the computer. And most people kind of stop. You know, most people, maybe they use high level libraries. Like a lot of programmers, they just use libraries and they're happy with that, and they stop there. And then some amount of programmers will actually start writing code that talks directly to the Linux kernel. And that is like the system call level. And I feel like I got really good at that level reading the Linux programming interface. And then further down from that, beyond the Linux kernel, is the instruction set architecture level. So these are actually writing machine instructions. And then a step below that is like, how is the hardware actually implementing the ISA? What is the microarchitecture? And they teach you a lot about that as well in this book. So there's a lot to digest in this book. I wouldn't recommend it necessarily as a blanket book for getting good at reverse engineering, but the skills that you will acquire if you actually go in and read some of this and understand it will be great for reverse engineering. If you go to my GitHub repo here, for the course CSAPP, there is a link here to video lectures. So if you scroll down here, there's like this results per page. Just put it at the max value. So these are all the, let's do sort by order. Yeah. So these are all the lectures for the course. So even if you don't do the reading, if there's a section of this course that interests you, I would at least watch the video lectures. That'd be a good way to like get some of this information. And in fact, everything from network programming onwards, I'm just watching the lectures. I'm not even going to be doing the reading, because like I said, I've already read so much about this stuff. I don't need to read more about it. I'm just gonna, you know what I do? I go into the lectures and then I just set the speed to like 2x.
Hey, welcome. Good to see you as always. Today we're going to
and just watch the lectures. So again, if you go, where is it? Yeah, if you go to my GitHub, it's under CSAPP and then video lectures down here. But yeah, been pretty busy since you took a break here from the chat. If I go back over here, another thing I've been doing is I've been publishing my streaming schedule on Proton here, because I want to be consistent in my streaming. I kind of felt like I fell off in my consistency. And so the plan is, and I've been doing this for 2 weeks or a week and a half now. I guess 2 weeks, about 2 weeks. But the plan is to get at least 3 streams a day in. And I haven't been really great about that the past couple days, but I'm working on it. I'm working on it. Another thing I've been doing is playing World of Warcraft in the evenings. Just because I want to take a break sometimes from this shit. But the rule is that it can only be my evening stream. So evening stream is for video games. I figured I'd rather just play on Twitch, like video games on Twitch, than like spend the evening, watching YouTube or something just in my living room. I think it's more fun to just like do the stream. How do I get out of this week? Yeah, week. Yeah. I have a link. But yeah, I need to publish the calendar. I haven't linked it anywhere on my social or anything, but I will do that. I got so much to do. There's something else I would need to do today, I forget. Oh, I was gonna do a meal plan. So you can see like most of my days I'm like going to the gym, I'm working out, I'm doing cardio throughout the week, doing hikes and stuff. So I'm staying active, I'm getting my exercise in, but where I feel like I'm really falling behind is on my nutrition. I hit my macros pretty consistently, but I'm not doing well as far as like meal timing and getting the right types of macros in. So that's another thing I wanted to do soon. Let me write this down. All right, I'm gonna publish my calendar. And then I need to do my macros meal plan. The Fight Club kind of locked in, yeah. Yeah, I mean, I'm trying. But I made so much progress. The thing that's really like motivated me now is like after doing this plan, I was kind of demotivated looking at this because I'm like, fuck, man, I spent, like nearly 2 months working on the Linux programming interface. And then now I'm going to spend another 2 months on computer systems, a programmer's perspective. And it's like I started scheduling these other books and courses and stuff that I want to do in the year. And I'm like, fuck, man, it's going to get to the end of the year and I'm only going to have this accomplished. It got me really like down. Even though this is like a good amount of things to accomplish in a year, I still felt like, fuck, man, this is like this. I feel like I'm not living up to my potential and my ability to learn. Like my ambition is so much greater than my ability. It is insane. And so when I looked at this, I was like super depressed. And that's when I started doing the calendar. And I'm like, fuck, man, I'm going to like optimize my days. Instead of giving my time away to like social media and YouTube and like all these distractions, every single day I'm going to get on these streams. And it's been working out pretty well the past couple weeks. And it's going to be to where I finish this book. Let's see. It is, if I go to the calendar here. Yeah, let's see. How many weeks did we have? 1, 2, 3, 4. 1, 2, 3, 4. So this was a week. So I'll be finishing probably by the now here needs to be right here right now. So I'll probably be finishing by second week of April. Because all I have to do is finish the reading for virtual memory, finish the lectures and the recitations, and then a couple of labs. And I'm being selective about which labs that I do because they're so time intensive. But I think I'm going to have at least 2 weeks where I'm ahead of schedule on this book. And if with this level of focus and commitment, I'm able to make that much progress in such a small amount of time, sustainably, if I can do that, I'm going to rip through this stuff. I'm going to get so much more accomplished than I have planned here. So I'm excited for that. What is the goal in the long term? The goal is to understand computers. That is the high level learning objective. I've thought about that. Like, what is my overall learning objective? It's understanding. And I think through understanding, we can do novel, interesting things with our life and make the world a better place. That's like the big overall picture. And I think one of the problems I have with AI right now is that so many people are using it to do things without understanding them. It's kind of like in Jurassic Park, where that like dude is like, you know, you got caught up in thinking that you whether you could, you didn't think if you should. And I feel like a lot of people just want to do things without understanding them. And I think that's going to lead to bad results. I don't think it's going to be good for us. I think AI is an awesome, powerful tool. But the second you let it think for you, I think that's when things start getting really shaky, in my opinion. And I see it all over the place. Like, people send me like GitHub repos that are completely vibe coded, and I'm looking through it and I'm like, the person who created this has no fucking clue how this thing works. And this thing's going to lead to catastrophe. And you already see it in like the quality in software products. Like Microsoft Windows is a complete fucking dumpster fire right now. Even GitHub. I mean, you know, Microsoft has done I'm going to give them credit. They've done a good amount of solid work on GitHub to make it a better platform than it was before they acquired it. But at this point, like, there's so much garbage on GitHub, not even just on the content side, but like with GitHub Actions and all of these bugs that they have and all the stuff that I've been reading, like, it's just not good. I feel like these companies just wanted to adopt AI because they thought that it would eliminate the need for human beings, instead of realizing that AI is a tool that can augment human beings' abilities to make them more effective, more productive. And so, yeah, that's what I think. I think right now there's going to be like a period of time where people have produced products and projects, software artifacts, that they have no understanding about how they work and no ability to gain understanding about how they work because they delegated it all to AI. So that's my general goal, is to like have a higher level of understanding of computer systems, demystify this whole thing, because all of this, everything about computers is understandable. We built every single thing. None of it is like something that was given to us as a species. Everything about computers is human built. It's all synthetic. It's all artificial. And so you can understand the whole fucking thing. None of it has to be mysterious. And so I feel like understanding is something that I want to focus on with my life. Understanding computation. Heterogeneous computing is like a big area that I'm interested in. Even AI, as critical as I am of like the use of AI, I feel like artificial intelligence, especially AGI, like actual artificial general intelligence, is going to be a huge part of our lives, you know, in the next coming decades. So yeah, I guess that's where I'm at right now with philosophically how I'm thinking about what I'm doing with my life. Well, I've never analyzed me like this way. I'm getting at why we need calendars in our lives. Yeah, man, like most of my career, I hated calendars. I hated calendars, I hated email, and I still hate email. I think email is bullshit. Like I never check my email, or I rarely check it. I check it for important things, but there's so much bullshit in email. When I worked in tech, I had 3 jobs which spanned the course of about 15 years of my life where I didn't check email at all. I would check email if my manager came to me and told me that I had to check my email. And I would do it for the thing that he was having me check it for and then stop checking it. Because email is just like so stupid. But I mean, I can't recommend it in general to like not check your email at work. But for me, I got away with not doing it. But calendars, I think, are a good tool. And I oscillate. You know, I go back and forth in how well I plan my time. This is a thing that they call time blocking. So if you look, we'll go forward to next week. You can see every single minute of my day has a plan. It doesn't mean that I have to like adhere to the plan. Like I can change the plan whenever I want. But there's an existing plan that I should try to comply with in order to achieve the outcomes that I want in my life. And so, yeah, they call this technique time blocking. If you Google for it, it's an effective technique. I like doing it. And I've oscillated back and forth doing it throughout my life. But yeah, I'm definitely sticking with it for the rest of the year at least. Hey, how's it going, Teresa? Or is it Teresia? What is heterogeneous computing? Heterogeneous computing is this concept of the computing environment for cloud environments or for data centers not being so CPU focused. So for most of my life, data centers are racks of CPUs, basically networking gear and CPUs, machines that run these big CPUs. Heterogeneous computing is saying there's going to be all these different types of hardware. There's going to be GPUs. There's going to be tensor processing units. There's going to be different types of hardware accelerators in the mix of hardware. It's not all just about CPUs now. And so when we write software, we're going to need to write software that can specialize into these different types of hardware to achieve the performance that we want. And when we write algorithms, the algorithms need to consider, maybe I'm not running on a CPU. Maybe I need to design my algorithms so that it can run in CUDA, it can run in Vulkan, it can run in SIMD, and all these other types of execution. So that's what I'm focusing on next, is this course on parallel computing. So it is a Stanford parallel computing. I already went through all the lectures on this last year, but they teach you, traditional multi-core processing, but then they get into CUDA. They have some stuff on SIMD. What else do they get into here? Yeah, a bunch of different stuff related to parallel programming. But I watched the lectured videos. They were really good. They're a little dated at this point. It's 2023, but they're really good. And I need to go through and do all the assignments basically. So that's what I'm going to be doing later this month and into May is that parallel computing course. Am I a college student? No, I'm not. Yeah, I'm kind of retired. I'm semi-retired now. I quit my job back in 2024, and now I just like study computer stuff all day. Do you know about graphics as well? I don't do much graphics, but this parallel computing course obviously is in the graphics department, graphics courses at Stanford. So we will be getting into that later on this month. I'm tempted to get into some graphical programming. I do have a bit of an arts background, but yeah, it's one of those areas that I could spend so much time in. I'd rather spend it in focusing on my overall learning objectives. So the parallel computing course is next, and then I have this book, CUDA by Example, which I think will dovetail nicely with the parallel computing course. And then I have some travel that I'm going to be taking some time off for. But then when I come back, we're jumping right back into programming the massive parallel processors. So this is an algorithms book that is focused on parallel computing and algorithms for parallel computing. So yeah, it's a lot of C. I think it's focused. Yeah, it's CUDA. But yeah, lots of. Oh look, I've implemented some of this recently. Matrix multiplication kernels. But yeah, that'll be after CUDA by Example. I'll be reading that book, and then I'm gonna be reading that concurrently with this book called Learning eBPF, which is by Liz Rice. I've not bought this book yet, but I think it'll be a good starter for me on eBPF because I've done a little bit of eBPF with BCC, the BPF compiler collection, and BPF trace. Like Neuronath and I played with that recently, a couple weeks back. So yeah, I have some experience with BPF, but I think learning eBPF would be a good resource. That's nice that you'll do that. Can I ask, why did you quit the job in 2024? And why are you not joining the job yet? How many chapters in this book? I guess, so I quit my job in 2024 because I had a lot of success financially that allowed me to quit my job. And I didn't want to work at the company I was working for anymore. So I just quit. It's pretty much as simple as that. And why did I not join the job yet? I guess rejoin the job market. And I haven't because I don't want to, and I don't have to. I'm in a pretty good position in my life right now where I have no kids, I have no spouse, I have no obligations to anyone other than myself. And I want to learn all this stuff, and I want to have the time to learn it. And when I'm working professionally, while companies want you to continue learning as you develop professionally, what I've noticed is that it's often subjugated to the higher priority, which is you getting shit done. Like companies want productive employees. They could really give a shit whether they're learning or not. So whenever you see like learning, continuous learning, or continuous education as part of like the core values of a company, you got to be skeptical of that. It has to be a really good company for them to actually live up to that. So yeah, I took the time off because I want the dedicated time to pursue my learning objectives and just to live life a little bit. I'm getting older. I want to experience some of the things of life that I want to experience before I get too old. And then he said, how many chapters in this book? So the book that we're currently reading is this Computer Systems: A Programmer's Perspective. I'm on chapter 9, and there is a total of how many chapters in this book? Contents. I think it's like 11, 12, 11. Yeah. Oh no, 12. Concurrent programming is 12. So we are on chapter 9 right now, which is virtual memory. And I am making some progress on reading this right now. So we got to 842, which is DRAM organization. Let's conclude this section because I gotta hop off here for dinner. I'm just gonna read the last part of this, and then there is a practice problem at the end of here, and that'll be a good place for us to stop. So DRAM cache organization. So this diagram up here just kind of demonstrates virtual to physical memory mapping. To help us keep the different caches in the memory hierarchy straight, we will use the term SRAM cache to denote the L1, L2, and L3 cache memories between the CPU and main memory, and the term DRAM cache to denote the VM's system cache that caches virtual pages in main memory. The position of the DRAM cache in the memory hierarchy has a big impact on the way that it is organized. Recall that a DRAM is at least 10 times slower than SRAM, and that disk is about 100,000 times slower than DRAM. Thus, misses and DRAM caches are very expensive compared to misses and SRAM caches, because DRAM caches misses are served from disk, while SRAM caches misses are usually served from DRAM-based main memory. Further, the cost of reading the first byte from a disk sector, if you have spinning disks, is about 100,000 times slower than reading successive bytes in the sector. At the bottom line is that the organization of the DRAM cache is driven entirely by the enormous cost of misses. That's worth highlighting. I think that's an important fact, is that the design of the DRAM cache, virtual memory DRAM caching, is entirely driven by the enormous cost of misses going out to disk. Because of the large miss penalty and the expense of accessing the first byte, virtual pages tend to be large, typically 4 kilobytes to 2 megabytes. Due to the large miss penalty, DRAM caches are fully associative. That is, any virtual page can be placed in any physical page. The replacement policy on misses also assumes a greater importance because the penalty associated with replacing the wrong virtual page is so high. Thus, operating systems use much more sophisticated replacement algorithms for DRAM caches than the hardware does for SRAM caches. These replacement algorithms are beyond the scope here. Finally, because of the large access time of disk, DRAM caches always use write back instead of write through. So I had already read this. I think this is where we left off, but I just want to refresh that section there. All right, so page tables. So I learned recently what page tables are, like at a concrete level, is they are data that's stored in memory, and there's multiple levels to them. And the data is basically where the mapping between virtual and physical addresses, basically. And that data resides in memory. And you think like, well, the CPU doesn't want to have to go out to main memory every single time it needs to resolve addresses. The CPU needs to be able to resolve addresses within the CPU. It can't go out to the memory bus. So what happens is the operating system puts all this mapping stuff into the main memory, and then the memory management unit that's part of the CPU has this thing called the TLB, the translation look-aside buffer. And that thing caches really aggressively the page tables from main memory. So whenever the CPU in kernel mode is updating the page tables, it updates the TLB as well. So that's my current understanding of things. That might be invalidated in detail as we progress in this chapter, but that's my overall understanding of things, is that the kernel establishes the page tables in main memory, and they're cached aggressively in the translation look-aside buffer so that the CPU doesn't have to hit main memory every time it wants to map virtual addresses to physical addresses. Okay, page tables. As with any cache, the VM system must have some way to determine if a virtual page is cached somewhere in DRAM. If so, the system must determine which physical page it is cached in. If there is a miss, the system must determine where the virtual page is stored on disk, select the victim page in physical memory, and copy the virtual page from disk to DRAM, replacing the victim page. These capabilities are provided by the combination of operating system software, address translation hardware in the memory management unit, and a data structure stored in physical memory known as a page table that maps virtual pages to physical pages. The address translation hardware reads the page table each time it converts a virtual address to a physical address. The operating system is responsible for maintaining the contents of the page table and transferring pages back and forth between disk and RAM. Figure 9.4 shows the basic organization of a page table. A page table is an array of page table entries. Each page in the virtual address space has a page table entry at a fixed offset in the page table. For our purposes, we will assume that each page table entry consists of a valid bit and a n-bit address field, probably 64-bit for AMD 64. The valid bit indicates whether the virtual page is currently cached in DRAM. If the valid bit is set, the address field indicates the start of the corresponding physical page in DRAM where the virtual page is cached. If the valid bit is not set, then a null address indicates that the virtual page has not yet been allocated. Otherwise, the address points to a start of a virtual page on disk. The example in figure 9.4 shows a page table for a system with 8 virtual pages and 4 physical pages. So let's take a look at it. It says 8 virtual pages and 4 physical pages. So we have our virtual memory, 1, 2, 3, 4, 5, 6. We have our memory resident page table, and then we have the physical memory. Okay, so in this diagram, the right-hand side, it's either your page is either resident in physical memory, or it's stored in swap space on the disk. So it's in one of these two sets here. And we have 8 different addresses. Some of these addresses are not used, in which case they have a valid bit of 0 and a null address. In the situation where the physical page is in memory, we have a 1-bit set to valid, and it points to physical memory. In the situation where it's pointing to disk, the valid bit is set to 0, and it points to disk. So pretty basic organization here. So that shows the system with 8 virtual pages and 4 physical pages. So you can see 8 here and 4 here. 4 virtual pages, VP1 through 7. Oh no, so 4 virtual pages, VP1, VP2, VP4, and VP7 are currently cached in DRAM. 2 pages, VP0 and VP5, have not yet been allocated, and the rest, VP3 and VP6, have been allocated but are not currently cached. An important point to notice about figure 9.4 is that because the DRAM cache is fully associative, any page can contain any virtual page. So that touches back to association of caches that we learned about when we studied cache lines in CPU SRAM caches. So associativity is basically a fully associative cache. Any element can be in any position in the cache. Whereas with like SRAM, you have a partially associative cache, in which case you have sets that kind of divide the cache up. So say you have 4 different sets, and individual cache lines are assigned to any one of those 4 sets, but it has to be, it's assigned one of the set, and it has to be in that set. And it cannot necessarily conflict with cache lines that are in the other sets. So that's partial associativity, where sometimes cache lines map to the same set because there's only 4 sets and you have 64 bits address space, so a lot of things are going to map to the same sets. That's the associativity part. But because they're split up by 4 or by n, usually it's like number greater than 4, that's why it's partial associativity, because there's these distinct separate sets that addresses map to. But it looks like with pages and page tables, they're just fully associative. There's only one set effectively. Cool, so that leaves us off at practice problem 2. I'm going to take a break here for dinner, and I'll be back on this evening. I'm going to play some World of Warcraft because I'm done reading for the day. But yeah, it was nice chatting. Tercia, it's nice meeting you. Nernef, it's nice seeing you again. If you want to watch me play WoW really badly, I'll be on probably in about 45 minutes after I get dinner here. But if not, have a good I guess morning your time. Cool. All right. See you later. Bye.